Hey, welcome to Organic Chemistry Part 2. We're going to be looking at physical properties, and there's actually a whole bunch of them that you need to wrap your head around. So the first one is melting points and boiling points of the substance. The second one, which is related to that, is what phase of matter it would be in at room temperature, say. So solid, liquid, gas, that whole thing. The third one is viscosity. Funky word, which basically is about how a substance flows, and it's about how difficultly it flows, if you know what I mean. So not its fluidity, but its viscosity. It's like how sticky it is. So water compared to oil compared to syrup, that kind of thing. Volatility is another one. Volatility. Now, something that's volatile changes easily. Volatile personality! You know, they fly off the handle easily like that. Volatility of a substance physically is when it changes state quite easily from liquid to gas, for instance. So we were talking about nail polish remover earlier. Propanone, very volatile substance. You leave the lid off that thing and it's evaporated within half an hour, kind of thing. Water is medium volatility. It's still going to be around there tomorrow, but it's going to gradually evaporate, that kind of thing. So that's volatility, which is also related to something called vapor pressure. Okay, which is, if you can imagine in simple terms, if you get your bottle of nail polish remover, when you open the lid, suddenly you smell everything because the vapor escapes. There's quite a high vapor pressure in there because it's actually evaporated. A lot of it has evaporated. So it's the amount of the substance that is in the air at the surface, in simple terms. So the greater something's volatility, the greater its vapor pressure. We'll leave it at that. Then there's solubility, and that's another physical property, whether something will dissolve or not. And in simple terms, I'll just give you that one is like dissolves like, but we'll come back to that in a minute. Now, there's the whole list. Rather than trying to get to understand each one in absolute detail and be able to explain it perfectly, let's go straight to the summary of things, where in fact these are all connected by one physical property, and this is where your explanations need to center, and that is IMF. And that's not the International Monetary Fund, it is the Intermolecular Forces. Okay, so Intermolecular Forces, those determine all of these, what intermolecular forces are going on. So your grade 11, where you started learning about shapes and polarity and dipole, induced dipole, London forces, hydrogen bonds, etc., etc. Now it's all coming to roost, because this is where you need to be able to explain stuff using intermolecular forces. So just have a quick look at then what are the factors that affect intermolecular forces. The first thing is the size of the molecule. So when we're looking at organic chemistry, you know, that's the context in which we're looking at these things. How big is the molecule? That is going to affect the strength of the intermolecular forces. So consider within a homologous series. Let's take alkanes, for example. Methane, ethane, propane, butane, pentane. Give me longer and longer and longer and longer. It's the same kind of forces in between them. There's non-polar as a molecule, so there's just London forces in between them, induced dipole. Not particularly strong. That's why methane is a gas, ethane is a gas, propane is a gas, butane is a gas. It's only when you get to pentane that it's actually for the first time a liquid. And it's getting longer and longer. The size of the chain is getting longer and longer. And what's increasing is, in particular, the surface area. I like to think of it like Velcro. If you stick two tiny little pieces of Velcro together, you can easily rip them apart. But slightly bigger piece, and then bigger still. Have you ever worn a Velcro suit? I went to a fair once. You put on this, I was actually quite sweaty from the previous person, that was gross. But anyway, you put on this whole Velcro suit and then you jump on a trampoline and you land on a wall. It's just great fun. Anyway, so the greater the size, then the more like little connection points there are, like Velcro, for one molecule to join to the next. So the longer the molecule, the more likely it is to bond to its neighbor. Okay, so size is important. And then the second thing is polarity. If you remember the whole thing of one side of the molecule being slightly positive and the other side being slightly negative. If we have a stronger polarity, on the different molecules, then the pluses will attract the minuses of another molecule more strongly. So we're looking for particular little makeups, parts of the molecule where strong polarity occurs. So let's have a look at a couple of questions to unpack that a little bit. Let's start with the whole polarity thing. I think you've got the idea of the size one. I'd like you to draw quickly whilst I'm going to scribble it down. Molecules, the structural formula for ethanol, and ethanoic acid. Okay, so ethanol, see if you can beat me there. It's eth, it's ol, that's it. Ethanol, it's also eth. You get that? And a bunch of H's. And ethanoic acid, it's eth. Now, as I said in the previous one, to really maximize this, if you are wanting to think these things through, you can always pause the video and do it before I do it. But because anyway, you got the idea. Those are our three compounds. The big question is, which one of those is going to have the highest boiling point, and which one's going to have the lowest boiling point? Well, they're all similar sort of size, so size is not really going to make a difference here, but it's all about polarity. Now, to identify polarity, you need to understand the electronegativity differences. So look on the table, look at the electronegativity differences. Let's take the one on the end here. Hydrogen, electronegativity of 2.1. Oxygen, 3.5. Carbon, 2.5. So the CHs, they don't really add much polarity. The difference in electronegativity there is only 0.4. Oxygen to carbon, well, that's a bit bigger. That's 1. But the OH, that's the big one. Okay, so that's the one that we're after. That's a difference of 1.4. That's the OH, and that is the CO, and that is the CH. So that's the greatest polarity in that one. This one doesn't have an OH, but it does have a CO. So we could say the difference in electronegativity is 1 there. And that one kind of has both. So it's got the 1.4 as well, which is the big one. And then it's also got quite a strong carbonyl group there. So in fact, bottom of the charts, if we start at the bottom, is going to be this dude. Okay, because he doesn't even reach the 1.4. In other words, this would push it into the realm of hydrogen bonding. This does not have hydrogen bonding. It's not quite strong enough for that. So that's going to be bronze medal. All right. Then it's between these two. They're both looking pretty good, but this one pips it at the post because of this extra bit of polarity that's going on there. So this actually comes up second with the silver medal, and gold medal goes to ethanoic acid. And if you want to get fancy in terms of explanations, you can talk about the fact that actually that forms a double hydrogen bond. So what we end up with is something like this, two neighbors. You get that kind of setup, and the H of this side is attracted to the O of that side, because that's positive, slightly negative, and the same here, positive, negative, and so you actually get a double hydrogen bond being formed, which means that that has the highest boiling point. Now the way that you explain that is you break it down, you say, right, this has the greatest electronegativity difference, therefore the strongest polarity, and 2 points where bonds can be formed, therefore having the strongest bond. So work through that explanation to get to saying that it's got the strongest intermolecular forces. Therefore, and this is the next point, so you've got one tick for all that blurb that I've said, if you can summarize all that. The next tick comes for the fact that you have to say, therefore, it needs the greatest energy to overcome those forces. And then the final point, therefore, has the highest boiling point. Okay, so you explain why it's got the strongest bonds, then say it's got needs the greatest energy to overcome them, and then say it's got the highest boiling point. That's the gist of how you would begin to explain something like that. And that about wraps it up for physical properties. So do a bit of practice on that one, and we'll move on to chemical properties just now.